Hi guys, today we're going to be going over gas laws. So the first law that we're going to be focusing on is Boyles Law. Now Boyles Law states that the volume of a fixed mass of gas at constant temperature is going to be inversely proportional to its pressure. So this is the equation for inverse proportionality. And if we remove this sign over here, this proportionality sign, we're going to add a constant which is going to be K. So what we're going to get is V is equals to K upon P. And then we get PV is equals to K, which is your equation over here. PV is equals to constant. So when you draw a graph of volume against pressure, you're going to get this shape, which refers to inverse proportionality. If you draw a graph of volume against 1 upon P, you'll get a direct proportional graph. And PV is constant. So since it's constant, no matter what value of pressure you put in, the value for PV is going to stay the same because it's constant. The second law is Charles' law, which states that volume of a fixed mass of gas at constant pressure is going to be directly proportional to its temperature. So if the temperature doubles, the volume will also double. If the temperature gets halved, the volume will also get halved, and so on. So because of that, similarly over here, if you remove the proportionality sign, you are going to get V is equals to KT, and V upon T is equals to K, which in this case is the constant that we have. Now, if you draw a graph of volume against temperature, this is what you're going to get. The y-axis refers to volume. Now, if your temperature is in degrees Celsius, it's not going to pass directly through the origin. Over here, this value is going to be room temperature, so it's going to be approximately 23 degrees. This is just an approximation. And it's also going to have a y-intercept, which is the room temperature, and it's going to have an x-intercept. Now, the x-intercept in this case refers to the absolute temperature, absolute zero temperature, minus 273 degrees Celsius. Now, according to this graph, if you extend it below, your volume will become negative, which is something that's not possible. So to solve this problem, scientists invented a new scale by the name of Kelvin scale. So according to that, if you made a diagram for the Kelvin scale, and the x-axis you had temperature in Kelvin, and the y-axis you had volume, it would be a straight line passing directly through the origin. So because of that, you would not have the negative volume effect that you're having right now if you extend this graph. Now, according to the Kelvin scale, this is the conversion. So temperature in Kelvin is equals to temperature in degrees Celsius plus 273. So for example, 0 degrees Celsius will be 273 Kelvin, 100 degrees Celsius will be 373 Kelvin, and so on. So you're going to start from 0 Kelvin, which is minus 273 degrees Celsius, which is the absolute zero temperature. So the last law that we have over here is Avogadro's law, which states that volume of a gas under ideal conditions of temperature, like all the other examples that we did also had ideal conditions. So this is a similar thing. So this volume is going to be proportional to the amount in moles of the gas. So we have V is directly proportional to N over here. N in this case refers to moles. Now we've done three laws. We've done Boyle's law, we've done Charles' law, and we've done Avogadro's law. So just a recap. This over here is Boyle's law, which states that volume is inversely proportional to pressure. This is Charles' law, which states that volume is directly proportional to temperature. And this is Avogadro's law, which states that volume is directly proportional to the number of moles. Now we're going to be combining these laws to form one particular equation. Now volume is directly proportional to the number of moles, which is N, which is this equation over here that I marked in green. Volume is also directly proportional to temperature, which I've marked in white. And volume is inversely proportional to pressure, which I've marked in P. Now, like we did in the previous laws, in order to remove this proportionality constant, we are going to be adding the proportionality sign, we're going to be adding a constant, which in this case is R. Now, R is an ideal gas constant, and the value for this is going to be 8.31 joules per Kelvin per mole. And this is going to be Again, the value is going to be constant and it's going to be stated in the data booklet, so you don't have to learn it. P refers to pressure. Now, pressure can be in pascals, kilopascals, and ATM, but usually in our syllabus, they don't really give questions related to ATM. But one thing that you need to know is that 1 ATM is equals to 1 into 10 to the power 5 pascals. And N refers to the number of moles of gas that you have. Temperature, T is going to be the temperature in Kelvin of the gas. So in questions, when they give you the pressure in pascals, you're going to take the volume in meter cube. And if they give you the pressure in kilopascals, you're going to use the volume in dm cube. Now, this is something that's very important and it's tested quite frequently, so it's important to remember to convert. Now, we're going to be taking a look at an example question of this formula. So the question is, calculate the volume taken up by 1 mole of an ideal gas at RTP. And the temperature they've given is 25 degrees Celsius. So like I discussed in the previous slide, if it's RTP, that means the pressure is 1 atm, which is going to be 1 into 10 to the power 5 pascals. The volume is unknown. The number of moles is going to be 1. R is always going to be 8.31. And the temperature, again, in the equation, which you use, which is PV is equals to nRT, the temperature needs to be in Kelvin. So even though they've given it in degrees Celsius, we'll have to convert it to Kelvin by adding 273 to it. So after you apply this equation, you're going to get this as the volume in meter cube.